Welcome. Welcome to today's HAO colloquium. Today we have Dr. Binzheng Zhang from HAO. Binzheng received his undergraduate and master degrees in electrical engineering from Zhejiang University in China, and his PhD is engineering physics from Dartmouth College, where he stayed on as a research scientist for a couple of years till 2015. And then he came to HAO as a postdoc fellow earlier this year. And his research interests include magnetosphere, ionosphere-thermosphere coupling, MHD, magnetic reconnection, and computational plasma physics. So today he's going to shed some light on a very dark and mysterious underworld.
Okay. Thank you very much for inviting me, giving a talk like this. And I kind of like to word this because this is from my advisor. If you know who he is, you know why he came up with words like this. Because I'm going to talk about some stuff we did in modeling the thermospheric uh, density and wind stuff, and it's a really special region of the geospace, and it's very important, and its temperature is very high. Okay, so to start with, I'm gonna go through basically these questions: is what is space weather, and what is thermospheric weather, and why should we care? Why it's important? And then the last question is how do we model it, or how do we predict it, or how these predictions can be used for kind of like operation in an operational sense. So to start with the space weather, and I think, which is probably right, that everything is originated from the sun. I was taught by teacher when I was like elementary school, everything's from sun, and it seems like this still works, even I'm doing space weather. So what's showing here is actually a cartoon movie made by NASA artist showing the connection between sun and the earth. And I'm gonna play it again so you can see that. Oops, where it is. Sorry. Yep, there we go. So here's the sun, and then we have quite a lot of mass ejected from the sun. Is usually called CME, coronal mass ejection. And when these mass reach the Earth, interacts with the geomagnetic fields and causing all kinds of phenomena. And this one is called magnetic reconnection, which brings electromagnetic energy and particles going all the way down to the atmosphere. And you see this beautiful aurora, and there's also energy flowing from the solar wind all the way to down there. And talking about the sun, and this is probably very well known that the sun has a cycle, which is called the solar cycle. And this is a plot showing the EUV imagery of the sun over 11 years, which is one solar cycle. And then people define these as solar minimum and solar maximum. So these white spots are actually regions with active stuff going on. And then with solar maximum, solar minimum, there's not much going on. And solar maximum, there's lots of activities going on the sun. And that's going to affect what's affected the weather in the geospace and everything down in the magnetosphere, ionosphere, and the thermosphere. So how's this solar cycle related to the storms we see in the geospace? And this is actually a nice plot, and actually showing the relationship between the solar activity and the geomagnetic storms and we see. And here you see that the horizontal axis is a year, and that's the sunspot number. More sunspot number means more active. So solar maximums will be here and solar minimums will be here. And then the blue bars are actually the solar flares, and you see there's a correlation between them. And if you go down to the geomagnetic storms, and you can see that there are quite a lot, there are more storms during solar maximum, while the activity is quiet. And the storm definition are based on the DST indices, which is measuring the disturbance of the Earth magnetic field on the ground. So say minus 200 nanotesla change in the geomagnetic field is very large. So that's a very intense storm. So you can see that we see this periodic, 11 years period of the solar activity and geomagnetic storms. And right now, it seems to be, we reach the solar maximum, but we don't have many storms, and even like there's no intense storms recently. And then, is there something wrong with the current solar maximum? Maybe your solar folks can tell me that. And I don't have a problem with that because we're not hit by the sun anyway, which isn't a bad thing. Okay, so how's the connection what's the connection between all the way from the sun to the atmosphere? And this is one of my favorite image, shown this so many times. And this is showing the Geospace System, which is the solar wind from the sun to the solar wind to magnetosphere and ionosphere-thermosphere down below. And of course, this figure is not to scale because the sun should be way over there. And if I do that, and you won't be able to see the sun. So the point here is that the energy, particle and electromagnetic coming all the way from the sun, interacts with the Earth magnetic field, forms this giant region called the magnetosphere. And then as you go down to the lower region, and that forms the partially ionized part of the atmosphere, which is called the ionosphere. And then there's ionosphere is strongly coupled to the region called thermosphere, and which is the main focus of my talk today. I'm going to go through the details, some of the details of the thermosphere very soon. So how does these space weather affect us, and why should we care? And this is actually a very busy figure. I'm not going to go through all the details on this figure, but just to go pick some interesting ones. So this is the Earth on the ground, and we have the atmosphere, ionosphere, thermosphere, and go way up at the magnetosphere. So these space weather phenomena affect us in various kinds of ways. For example, we have if you have astronauts flying in the geospace, say several Earth radius, and they might be exposed to radiations from very high energy electrons and protons, which is called radiation belts. And also the spacecrafts and satellites are exposed to the solar protons, which cause damage to the solar panel. And also, if you go down a little bit, and then the magnetosphere ionosphere current closure will cause disturbance of ionosphere currents, which affects the plasma distribution in the ionosphere, which affects the communication coming from below, if you're communication. And also, the low Earth orbiting satellites flying in this region, thermosphere region, will see the air drag from the atmosphere. So that's actually a very important process. And then going down to the ground, and if we have, during geomagnetic storms, the ionosphere is very disturbed. There are going to be lots of currents flowing in the ionosphere because these are ionized plasma. And the currents can cause ground-induced currents, according to Maxwell's equation. And then those currents will be induced in a scale of tens of kilometers to hundreds of kilometers, which are like pipelines, oil pipelines, or power grids. So these are also phenomena affecting all of us. And I'm not sure how much the air flying passenger, what I was told, is probably very safe. It's not affected by space weather much. So the region I'm interested in for today's talk is actually the ionosphere-thermosphere region, way here, which is above the lower atmosphere, and it's a partially ionized atmosphere, and with the thermosphere, and then the effects mostly affects those satellite operations flying in this region. So let's take a look at the characteristics of the thermosphere region. So first, this is actually a vertical temperature profile of the thermosphere. It's a very general vertical, and you can see that you have all different regions. I don't know why my ionosphere went to mesosphere. It should be somewhere here. So the region I'm interested in is actually above the meso. Okay, fair enough. Mesosphere, and then you can see that the temperature goes very high, usually to like in the order of 1,000 degree of Kelvin, and the altitude is usually above 100 kilometers to 1,000 kilometers. So that's the region I'm interested in. So the energy sources of this region has met multiple energy sources from, say, EUV radiation from the sun, and joule heating from the magnetosphere, ionosphere, because the ionosphere plasma are connected to the magnetosphere, which will causing the collision between the charged ions and the neutrals. So the collision means energy exchange, means heating. So we call this joule heating. And also particle precipitation from the solar wind magnetosphere, as the movie just showed. You have the particles from the solar wind through the magnetosphere and go out down to the thermosphere region. And also other dissipations from the upward propagating waves like tides, gravity waves, planetary waves. So the thermosphere is actually driven by both drivers from the top and bottom. And there are energy sinks for the thermosphere, for example, thermal conduction, different coolings from different ions, and also chemical reactions. So why is this thermosphere very important as a sphere? We have, as I mentioned a couple of times, we have satellites flying in this region, and that actually determines the orbit of those satellites. And we want to know what's going on there. We want to know how do we model this, and what does all the drivers affect the dynamics of the thermosphere. So here is a very nice plot showing you the variations of the thermosphere. So if you look at these two curves, so these solid curves are actually temperatures of the thermosphere, vertical profile, altitude, and temperature. And you can see that during solar minimum and solar maximum, the temperature can vary about 100%. So that's a very large variation of the temperature. And the dashed lines are actually particle density. So these are particle densities. If you're talking about, well, close enough, particle densities, and the particle densities can vary even more than 100%, usually locally at high altitudes. So the mass density can be enhanced by like a factor of 3 or 5 between the solar maximum and solar minimum. So there are a couple of time scales about the variation of the solar thermosphere. Usually the solar cycle, of course, because the solar radiation is changing every 11 years. So the thermosphere has a variation of that cycle. And annual variations, because the Earth is rotating around the sun. You have the winter, summer, and the winter and summer, and that's another one. And 27 days is actually the rotation of the sun. So the sun has a rotation period, because the thermosphere see different parts of the sun, and we'll see the variations, and also day-night variations, because there's this it's a part of the atmosphere, and there's more, and depending on the different scales, because if you have a geomagnetic storm, and then the time scale depends on the driving of the storm, and there are other things. So the idea is that the thermosphere is actually a very dynamic region of the geospace, which has a very important application to satellite tracking. So we want to know have a clear idea of what's going on and what's driving it, and how do we model it. And the reason for this is these are some very interesting plots. So this one is actually from NCAR, I think. So where's my equation go? So this is actually a plot showing you the satellite tracking problems during the March 1989 storm, which is a very big geomagnetic storm which caused a blackout of Quebec, Canada, for days. So the yellow curve is actually the AP index showing the activity level. So we got very high activity level here. And then soon after the geomagnetic storm happened, and the number of satellites that's not tracked well increased by a factor of 3 or even more. So which gives the question, so you want to know what's going on. Apparently something's affecting these satellites. And this is actually a plot from the orbits, high altitude of the orbits of the ISS after the October 2003 storm, which is known as the Hollow Wind Storm. And you can see that This yellow one shows the orbit change of the orbits during the storm, and that's one the after the storm. So you can see that before the storm, the orbits are pretty steady, and when the storm's going on, and after the storm, and the orbits decaying, and in some rates, and this region is mainly because we have during a storm there's so much energy coming from the sun all the way to solar wind through the coupling of magnetosphere, ionosphere go all the way down to the thermosphere and change the mass density, change the winds, and just change all the whole region. So the reason we want to see, kind of like I lost my equation. So the idea here is, this is a cartoon drawing show that's why the thermosphere, what the thermosphere does on the satellite tracking, is that if we have satellite flying in the thermosphere region, 400 kilometers usually, and if we have air drag, which is a force acting on the satellite and is proportional to the mass density of the atmosphere. So we have with the drag, and the satellite orbit's going to decay and slowly and going down. Without drag, it's going to go through the orbit as it's designed. It's either circular or something else. So the point of this equation is supposed to be here. The point is that the air mass density of the thermosphere determines how much drag force is on it. So if we want to track the satellite orbits, first thing you want to know is what the thermosphere density look like, or temperature, or other things. So this is why we are studying. And yep.
So does that plot, the log satellite plot, mean that the system takes about 10 days to totally recover or something?
Yes. Well, not. The satellite system takes days to recover, but the thermosphere, the thermosphere depending on the different conditions of the storm, different properties of the storm. So the recovery can be days. So it's not necessarily always 10 days. Yeah.
This is how long it takes to find the satellites again. The recovery is probably 2 or 3 days.
Yeah, it's related to the thermosphere recovering, but yeah, depending on the condition. Okay, so talking about this dynamics, and this is very important, and it's where the energy coming from. So as we discussed before, it's coming from the sun, and through the solar wind, and the solar wind transfers energy through the coupling between the magnetosphere, and there are going to be particle energies and electromagnetic energies, and those energies will be deposited to the Ionosphere-Thermosphere system as drivers, and which changes the density, mass density, and winds and temperature, and even more. So these are actually the drivers from the geospace. I would call them from the above. And then there are other drivers from the atmosphere below, as tides and waves we discussed before. So these are drivers from the below, and then that's causing the disturbance of the thermosphere as well. But today, I'm going to mainly talk about the drivers from the above. That's what the research work we've been working on. And this is definitely very important, but I'm not going to go through the details of that part today. So the reason we want to know do this kind of coupled study for the thermospheric modeling is, what if we got hit by a storm like this? So this is actually a very interesting paper by Baker et al. 2003. So this is actually a simulation from a numerical simulation showing the density and the velocity of the solar wind from this CME event. So you can see that the Earth is right here, and then so we just got lucky, and this CME storm just missed the Earth. So we did not get hit by this large CME storm. So the thing is that this actually happens a lot in the geospace system. So the question is, we want to know how we're going to do when we got hit by a storm like this. So we did not got hit by the storm did not got hit by this CME. Doesn't mean that we're not going to hit by it anymore. But the question is what the thermosphere ionosphere response, and what your satellite system going to respond to all these. And this is the This is actually the motivation of all these numerical modeling of the coupled system. So to do the modeling of this problem, we usually have two ways. One is you go through empirical models. They're depending on data, and they're very easy to use, can do real-time prediction. You just get you get some kind of empirical relation between the driving conditions and the distributions. And they usually do a very well job of describing the average state of the system because they're empirical natures. And also for storm time event-based modeling, and the empirical models can be, it's hard for empirical models to do the very accurate modeling. So the other type is physics-based models, which I'm working on, is that they're based on first principle physics numerical methods. And the physics differs between different regions. So you have to be solving different equations in different regions. And they're usually computationally expensive, requires times to finish the computation, which means for real-time predictions, it's going to be tricky. For example, we observe the solar wind parameters at L1, which is 30 RE, and then it gives us about a couple of minutes to calculate what's going to be down there if there's a storm. So that's going to be very tricky. And if your model does not run fast enough, you probably don't have a prediction at all. So, but these physics-based models can do reasonable jobs for storm times, sometimes, depending on the characteristics of the storms. And then recently, people start to develop these physics-based models based on different regions. So you have solar wind models coming from the sun to the Earth, and we have magnetosphere models coming all the way down to the 2RE. And then we have Ionosphere-Thermosphere models, which is the AIM group working here. So they are all they are global models, but they are actually regional. But nowadays, I think the modeling effort is moving towards the coupling between these large-scale models. So which is basically the main focus of my study. So before I start to talk about results, I want to show you some modeling stuff that we do in under the SISM framework. So this is actually a nice picture of the models we do. And what you see here, this is actually the inner heliosphere. And that's the sun. That's actually the origin of all the space weather phenomena. And you see that we have global models for the solar wind. You got nice flux ropes, CME coming out. And when they entering the Earth, and we go down to the magnetosphere model, which is based on magnetohydrodynamics, MHD. So the outer region of the magnetosphere model is actually MHD. So you see the bioshock, you see the magnetopulse, you see KH and flow channels, all things. And then the inner region is actually dominated by drift kinetics, which MHD cannot model. So we have other ways to incorporate that drift kinetics. I'm not going into detail about these. And then if you're going all the way down to the Ionosphere-Thermosphere, so we have these models describing the evolutions of the ionosphere plasma and thermosphere neutral gas. So these are actually the coupling model in the SISM framework. So it's kind of like a cool movie, just give you a sense what the region of those models are and what the physics are there. So this is actually the heliosphere model, and we call it LFM helio. LFM stands for Line, Feather, Mowbray, and Line is Professor Zhang Line, and Feather is one of his main collaborator, and that's just a name in the air. I don't think anybody met him.
Clark was a guy back in the day.
Oh, you met him, right? Oh, okay, I never. Okay.
He left to make money doing genetic programming for the Human Genome Project.
Okay.
So I assume so.
Sending me an email. Okay. So the solar wind modeling here, we're looking at starting from 20 RS is the solar radius to 1 AU. So the Earth is somewhere here, and 20 RS. The reason we picked that is that solar wind is in supersonic conditions, so it's a supersonic inflow for the model, so everything's a lot easier. And so the equations solved here are magnetohydrodynamics, MHD equations. And to finish a calculation for a model like this is going to require hundreds to thousands of processors, so it's very computationally intensive. So when you get down to the magnetosphere level, And then what you see here is actually a simulation of the southward IMF hitting the magnetosphere. So this is where the Earth is, and then these are magnetic field lines on the day side to the night side. These are solar wind field lines, and you can see that we have this nice shock, and then this is actually the boundary layer called magnetopulse, and there are all kinds of KH events going on, flux transform events going on, and what's more interesting is that this is called the so you see all these KH going on, and you see this in the magnetotail reconnections coming, and then these are actually flow channels, and people call these dipolarization fronts. So what happens is the field lines were stretched here, and they try to become dipolar. So that's all the dynamics here. And we also have incorporated inner magnetosphere physics by coupling a physics ring current model in this region. So this is actually the global magnetosphere model using the same solver as LFM. So the equations are a little bit more complicated because these are multi-fluid equations, can handle different ion species. So each ion species has their own mass, momentum, and energy equation, and plus Maxwell's equation. So the domain of the simulation is usually from 30 RE at one point and to 300 RE way in the tail. And then the modeling, this model does model the interaction between the solar wind and magnetosphere, and we also have the ionosphere down there. And then for this kind of modeling, and the computational usually requires hundreds to thousands of processors, so these are also very expensive simulations. And the drivers for this model is actually the solar wind conditions. So coming down even more to the lower region, and this is actually the Ionosphere-Thermosphere modeling, and most of you are very familiar, even familiar more than me on this stuff, is actually the TIE-GCM model, Thermosphere Ionosphere Electrodynamic General Circulation Model. So this model actually solves equations for the neutral gas and hydrostatic equations for the neutral atmosphere, and fluid equations for the plasma, and both of them are coupled through different processes. And what you see here is actually the variation of neutral density, neutral temperature during a storm. I think this is the St. Patrick's Day storm last year. It was KP 8 or 7. It's a pretty intense storm. So you see all these variations of the mass density, especially on the high latitude, because there's energy coming in. So this model is driven by solar radiation, magnetospheric energy, and particle inputs. And for this standalone model, these are empirical relations. So we just tell the model what the aurora particle precipitation look like, what the high latitude plasma convection look like, rather than using physics-based specifications. So what I'm doing more is we are gonna move it one step forward, is by coupling all these things together. And I think Mike's done coupling everything together, but I'm not gonna talk about that today. What I'm gonna show you, we're gonna couple the magnetosphere model with the Ionosphere-Thermosphere model, which is called CMIT, coupled magnetosphere Ionosphere-Thermosphere model. So this is how the coupling being done. So we have the LFM global magnetosphere model, which solves the interaction between the solar wind and magnetosphere ionosphere. And this is the TIE-GCM model, which solves the three-dimensional dynamics of the Ionosphere-Thermosphere system. So the coupling between them are actually very easy conceptually. So the magnetosphere model calculates what the plasma convection is at high latitudes and what the particle precipitations are as input to the Ionosphere-Thermosphere model. And then the TIE-GCM model, based on these inputs, calculate the ionization rate, calculate the collision frequency, everything down there, and calculate what's the height integrated conductance are in the ionosphere. The conductance model are used in this two-dimensional coupler, which solves the current closure equation between magnetosphere and ionosphere, and give the lower boundary condition for the magnetosphere. So what happened is that the magnetosphere calculations stop here, and then I give all these drivings to the ionosphere, and then all this coupling solves the equation to tell what the plasma circulation is down there as a boundary condition mapped to the magnetosphere. So this is a self-consistent coupling. So there's energy and particle particle energy and electromagnetic energy going all the way from the solar wind M and to I and T. So this is the model I'm going to talk. All the results I'm talking about is going to be based on this model or based on the extension of this model. So I'm going to show two examples today. One is the mass density modeling for a very large geomagnetic storm, and compared to satellite observations. And there's another one is the neutral wind modeling for a quiet time period based on the balloon observations made by Dr. Chen Wu here. So to start with, the August 24, 2005 geomagnetic storm is actually a very large storm. And if you're familiar with this, there's these parameters, and then the KP goes all the way to 9. So this is a very, very severe storm. So what you're looking at is actually the data from the CHAMP satellite, which is a European satellite. And then this is the time, and this is the measured mass density. And it's actually very low, 10 to the minus 12 kilogram per meter square. I think the density in this room is 1 kilogram per meter cubed. So you see this day-night variation of the density, and on top of them you see these spikes. These are very large spikes. And if you look at where are they, this is the magnetic latitude, and those spikes are usually at very high latitude in the polar region. So the indicates these are actually energy coming from the magnetosphere down to the thermosphere and causing the changes, all these spikes. So density varies a lot. And then if I don't have that, but if I plot something like from an empirical modeling, and then the empirical model is just going to do all the way, it's going to miss all these spikes. So that's why we want to see what if we use physics-based models like TIGCM or CMIT, how can we do any better than the empirical models? So this is going to be my next slide. So this is just the black curve is just a reproduce of the data from the previous file. And you can see that this is time, and this is the mass density at CHAMP, which is about 400 kilometers altitude. And you can see that the blue one is actually a standalone TIGCM simulation driven by empirical magnetospheric specifications, while the green one is actually the coupled model results, which means that the particle precipitation and the electromagnetic energy to the IT model is given by the MHD magnetosphere model. So you can see that compared to the data, and the standalone TIGCM kind of captures the baseline variation, long-term variation, but misses most of these spikes. And the reason is because that empirical specification of the energy and particle for such a severe storm is probably not enough. Okay, so then we look at the coupled model with the physics-based magnetosphere, and you see that it's doing pretty well for, it's capturing these spikes mostly, and doing better than, modeling the dynamics is better than the standalone IT model. But there are also problems that because these spikes are way overestimating those ones. So which means that the energy input, the physics-based model is probably giving too much energy going down to the thermosphere, ionosphere. So what's missing here? And that's a question. When you see something, don't match the data, which means that something interesting is going on. So one hypothesis we have for this event is that, so in the coupling picture, we just have the in this coupling picture, we have the basically we only have the electromagnetic coupling through the magnetosphere to ionosphere based on the current closure. But there are important things going on, such as, for example, ionosphere is a rich plasma source, which is partially ionized, and you get so much energy goes in, they're stuff that gonna come out into the magnetosphere, which is called mass coupling. So this is actually a phenomenon called ionospheric outflow, and this is actually a idea. So we have solar wind, we have energy goes in, so the ionosphere is going to have ions escaping the Earth gravity and go all the way into the magnetosphere, populating the magnetosphere, change the current system, change the electrodynamics of the magnetosphere, which will change the redistribution of electromagnetic energy deposited into the thermosphere. So these are actually interesting plots from observations. So you see this is actually the electromagnetic energy going down to the ionosphere. And these dots are actually the outflow coming out from the ionosphere. You see that have more energy goes in, you have more energy goes in, and you have more outflow coming out. So for a storm like a KP9, you got thousands of gigawatts energy going down to the ionosphere. They're going to be oxygen ions, hydrogen ions coming out from the ionosphere, populate the region. So that dynamics is actually missing in the standalone coupling picture. So what we do here is that based on the multi-fluid capability of the magnetosphere we have, we can put some relation like this in the CMIT model to model the effects of these oxygen ions or ionosphere ions coming during the storms and see what's going to affect the region. So this is probably too much detail, but the basic idea is that we have the LFM multi-fluid, which is MF is multi-fluid LFM driven by the solar wind. We calculate the energy input to the ionosphere system, and based on empirical relations, as I just showed, we just draw. So you just draw. Okay, so this is how much energy I get, and based on the satellite data, so this is how much ions coming out. Then we put the ions into the lower boundary and let them go out in the magnetosphere. So this is a very poor man's method to kind of count for the effects of ionosphere ions. See if we have these ion population for this storm, what the results will look like. Yes?
You used the word lower boundary a couple of times. Is that altitudinally low, or does that mean latitudinally?
Oh, I'm sorry. That's actually the altitude. So it's the low altitude boundary of the MHD calculation, because MHD does not have all the physics go down to the ionosphere, so the calculation stops at 2 RE, geocentric, so 1 RE altitude. So I call this 1 RE altitude as the lower boundary. It's actually low altitude boundary. Yeah, thanks for pointing that out.
This relation, you said you're going to maybe apply an empirical flux.
Yeah.
Outflow flux going back to the magnetosphere model. Is that flux also applied to the TIGCM?
No, because the ion, these ion population are actually usually accelerated in the top side, which is above the TIGCM domain, and then TIGCM does not have the physics to handle the dynamics of this population. So we kind of it's not completely self-consistent. So the idea here is just to see if I have this population in there somewhere, give some amount, and what it's going to do to the energy budget in the system. So that's the first step. And we have collaborators working on physics-based models to model this population, and we've made some progress on that as well. But I don't have that for this event. So here's the results we're coming from. So this is the same plot, but I replaced so the black is actually the CHAMP data, observed the neutral density along the CHAMP orbit. And the red one is actually the CMIT simulation with this ionosphere outflow population. So what you see that here is we're doing much better compared to the previous coupling method when outflow is included in the simulation. So this is actually a very interesting phenomenon, because if you look at the orbit averaged, the comparison, so this is time, this is orbit averaged mass. So what I do is I average the CHAMP density every orbit and plot them as a function of time. And you see that the black is data, and then the blue one is actually standalone TIGCM simulation. It's actually doing a pretty good job, capturing the basic variation of the mass density. But for these peaks, and then the CMIT model with this outflow population does the best, because it's probably the most closest to the physical condition during the storm condition. And you see that without the outflow, we got overestimation of the mass density for this particular storm. So these are just some averaged mass density distribution for different KP conditions. You can see that for higher driving, you got more density coming down in the polar region. So the idea here is actually pretty clear. With outflow, we do get a better distribution of thermospheric density, and that's mainly because it's changing the distribution of, yes?
This may be a stupid question, but are you using the orbit average to drive the outflow and then recompute it, or you just have a certain outflow?
I don't use the.
You update it every orbit.
So the outflow is actually calculated from the electromagnetic energy simulated in the magnetosphere model. So the empirical relation is from some other satellites. So I just calculate how much electromagnetic energy from the magnetosphere is and convert it to a outflow flux and put it in the magnetosphere. So it's not using and this orbit average is they only measure the neutral density. They don't have that information. It would be nice if they have the observation of the outflow flux. And I did more comparison on the distribution and the flux of the outflow, and they do because it's from the empirical relations, so they do kind of give you the range where the outflow is. So it's not like I'm adding a ridiculous amount of outflow. So okay.
How do you find DST?
What?
How do you find DST from the KGCM?
Oh, this is DST is from CMIT. It's because I have all the fields and currents in the magnetosphere, so I just do a Biot-Savart law to get the disturbance on the ground. All right, so this is what happened. So in the runs with outflow and without outflow. So what happened here is actually the outflow populates the inner magnetosphere, gets heated in the tail, populates the inner magnetosphere, enhances the ring current, which changes the current closure. So this is actually a current. Field line current goes out to the ionosphere, into the ionosphere. So you see it's actually improving the current distribution in the system, which improves the Joule heating, because Joule heating is actually J dot E, so which causes much less heating in the polar region. So without this outflow population, most of the energy going through the polar region and cause the overestimation of the neutral temperature and density. With this outflow, we had a better region 2 currents, have more energy going to the sides, and reduce the amount of heating and improves the mass density modeling for the thermosphere, because the Joule heating is driving the changes in temperature and the density. So this is actually a self-consistent kind of feedback loop in the coupled system. So I have a very busy movie here showing you what the dynamics look like. So this is actually the simulation from the storm. So what you look at is the magnetosphere. These are the ionosphere Joule heating and particle heating. And this is the thermospheric mass density at 400 kilometers for northern and southern hemisphere. So you see that, so this is a total mass density. And you see that as the driving condition becomes really high, and we got all these oxygen coming out and populating the magnetosphere. This is the XZ plane, and this is the equatorial plane. And after the storm, it's got mostly dominated by O+, and changing the distribution of the electromagnetic energy, and change the energy budget in the system, and for this particular event. And you see KP goes to 6, and it got hit, and it got some outflow coming out, and then it's going to go to 9, and got hit by really large IMF, and it got this oxygen ion plumes coming from the day side and night side, and populating the inner magnetosphere. And this is actually the mass density, and that's actually the satellite. And this is actually the comparison between the measured density and the simulated density. And we still have some large discrepancies here is at a very in the equator region, and that's probably related to the traveling of these thermospheric disturbance, and that's something to look at in the future. So besides this is storm time dynamics, and this is actually the quiet time modeling from that. So this is actually a very interesting experiment from Dr. Chen Wu, and using the balloon observation. So what they do is that they have balloon flying across the Greenland and across in the high latitude and measuring the neutral winds. And what you see here is actually the meridional winds. And this wind is actually it's kind of like a mystery. And what's going on is because you see that the winds are negative. Negative means they're going equatorward. Positive means they're going poleward. So as we would expect, the neutral winds on the day side would usually be poleward because of the day-night pressure gradient. You have hotter atmosphere and cold atmosphere, so winds going all the way to poleward. But what the measured winds are actually going equatorward. So something is going on. And what's interesting is that if you run the TIGCM driven by empirical magnetosphere, and you got this polar wind all the time across the day side. So this actually raises a question. So is there anything else going on for this event? And I'm going to skip this. Then we come back to look at the driving conditions. It's actually not a active storm time conditions, because you would imagine that if you're in storm time, the winds might be going anywhere because they're driven by this huge amount of energy distributed everywhere in the high latitudes. But this is actually a very quiet time. So the KP for that day is about 2. And except there's only one southward turning of the IMF at 8 o'clock. And most of the IMF conditions are positive, BZ positive, which means the coupling between the solar wind and magnetosphere is very weak for this event. And since that we don't have success simulating the equatorial wind using the TIGCM model, so we were thinking that maybe we should look at physics-based magnetosphere driving. So we turned to CMIT, and this is what CMIT is telling us. So if you look at these, and so the red dots are actually the measured meridional winds from the high wind balloon experiments on that day. And the blue one is actually the TIGCM driven by the Helios empirical model, which is one empirical model for the ion drift at high latitudes. And the yellow one is actually a Weimer model driven. So both of them are driven by empirical models. And the green one is actually CMIT. So the TIGCM is driven by LFM based on the coupling there. So it's very quiet. So ionosphere outflow is not considered in this event because there's not much outflow. So it's just a standard coupling between them. So you can see that in this event, if we look at CMIT and the comparison between the CMIT and the observation is much better compared to the other two driven by empirical models. And although we have some discrepancies on the day side, on the daytime where the southward turning of IMF could be related to those mesoscale, small scale heating processes, we can't model. But in the afternoon section, and then the winds are doing very, very much better compared to the empirical models. And these are the zonal winds are also, the CMIT are also doing better in the zonal winds. So we're trying to see, okay, so it seems like the physics-based magnetosphere does have a very big improvement on the modeling of the winds, even during quiet time. So we want to see what's really going on. So here's what's going on. So in this event, these are snapshots of the simulation from the 3. So these are TIGCM driven by empirical models, empirical ion drift at high latitudes. This is the CMIT driven by the LFM convection at high latitudes. So what you see here is at 13:30, basically that's a typical snapshot in the afternoon, is that you see the physics-based model gives you a convection cell which is confined in the open flux region, which is called the magnetospheric lobe cell. So these lobe cells are circulating in this direction, and you have a sunward ion convection which drags the neutral wind all the way to the equator. So the arrows are the neutral wind. So these contours are the ion E-cross B drift contours. So the ions drifting along these contours while the neutral wind direction is in there. So this is actually showing that this is actually an excellent example of magnetosphere, ionosphere, thermosphere coupling during quiet time. So even during quiet time, the thermosphere is strongly coupled to the magnetosphere through the plasma circulation in the ionosphere. So then you look at empirical driving conditions. The Weimer model is actually doing pretty well. It's trying to locate a lobe cell somewhere here, but the spatial extension and the direction of the ion drifts are not as accurate. I probably shouldn't use accurate, are not the same as LFM. So it's trying to drag a wind somehow in this direction, but not sunward. While LFM just has an ion drag all the way towards the equator. And the HELIS model is not doing anything because it doesn't have any lobe cell configurations. So we try to see if this is real or it's just a model effect. So I came to Dolores, who has the data from DMSP. So this is actually the simulation at 1330. So the contours are E cross B drift contours of plasma. And the green one is actually open-closed boundary. So equatorward of that, the field lines are closed. And poleward of that, the field lines are open. So you see this little cell, which is actually a lobe cell. So which means those flux tubes are rotating in the open flux region. And then they have very intense sunward plasma drift in this picture. And then we came to, if you look at the DMSP F16 pass, slightly after this, because this condition, this is instantaneous one, but the whole afternoon looks like something like that. So if you draw a plot, look at the DMSP ion drift, you see this is the cross-track drift. You see very intense sunward plasma convection and anti-sunward convection, which means there's possibly a lobe cell formed during this event. So this kind of comparison gives us some confidence that the LFM is doing more reasonable job on placing the ionospheric convection for the thermospheric wind dynamics. So this is actually a very point that even during quiet time, and then the physics-based modeling are still needed. So this is actually the simulation and from that event. I'm looking at the CMIT and then the TIGCM standalone driven by the Weimer model. And you can see that the color is the potential, the contours are E cross B ion drifts, and the arrows are neutral winds. So you see at the afternoon when the lobe cell forms, and you see the neutral winds are dragged all the way towards the equator. And the Weimer model trying to do something like that, but you can see the time scale and the variation, temporal variation of the Weimer model is not the same as LFM. If you do compute an average over all the day, and they're actually similar, so the difference between like 15, 20%, but actually the dynamics really matters because that's actually you need this physics-based specification at high latitude to get the winds or temperature or something accurate to a time scale like hours or even shorter. So this is the main point of this one, is showing the strong coupling between the magnetosphere, ionosphere, all the way down to thermosphere winds, even during quiet times. So I'm going to summarize some of the stuff I talked. As we talked, the thermosphere is actually a very important region because it affects systems, space systems such as satellite tracking, satellite drag. So we need to understand what's going on, what affects the thermosphere, what drives the thermospheric density, temperature, and all these things. And physics-based numerical modeling of the coupled system are very promising. So we just had two examples to show that both for a geomagnetic storm and for quiet time, the physics-based models can do better than either empirical model or standalone regional IT models because we have more physics incorporated in. So the take-home message here is thermosphere dynamics is very important, and modeling that has a very large potential application and interests for different communities. And if you want to get the prediction right for event-based, for example, like a huge geomagnetic storm, and we need to get the coupling between the solar wind, magnetosphere, and ionosphere. The physics processes, the chain of the processes considered in this coupled picture to get the thermosphere right. So that's the main point. And there are a couple of future works I'm going to mention very quickly. And this is actually the famous movie from Dr. Hanli Liu showing the gravity waves from below, and these are the meridional winds at 100 kilometers altitude. And this is the event, is a simulation showing there is a hurricane here. So you see all these disturbance from the lower atmosphere, and so one of the next step to do is that you need to consider what's this going to do to the thermosphere up there, because the wave's going to go up and disturb the boundary, and they're going to propagate up, it can amplify it and interact with other things. So that's one thing to consider. I think this is one of the main efforts being here in the AIM group is around the Wacom X model for this. And for me, one of the, another future work more interesting to me is actually incorporating more physics in the global magnetosphere. So for example, the ionosphere outflow is one of them. So we have outflow and we improve the prediction. So this is actually something I'm currently working on, is that to trying to add in drift kinetic physics to global MHD instead of coupling a ring current model. So what we do here is we use the multi-fluid equations and we calculate the temperature-dependent drift speed for each fluid, and then we make a correction to the fluid in the inner region. So instead of doing a single fluid calculation, we will decomposite a fluid to, say, 100 channels, and each channel has its own temperature dependent. And then we calculate what's the temperature dependent drift speed is, which is a small term, and add them to the system. So basically what we're doing is that we are creating a three-dimensional ring current model. So that's based on this three-dimensional ring current model, then we can study the self-consistent way of how those oxygen ions get energized, how's ring current formed, and then hopefully this improved MHD model can provide better understanding on the energy distribution to the lower IT system. And these are just very initial examples of the thing that we do with the drift correction and without the drift correction. You see something like a ring current formation, but there's way more work to do here. So I think I'll just stop here, and thank you. For questions.
Yeah, this might be a question more for Qian. You showed in your
I'm not here.
in your neutral wind that there was an ion drift that was also equatorward. Was that ion drift ice cap or where?
That's correct. I was going to ask how the EO model compare with ice cap.
It provides the best ion drift among all the models. I don't have a plot here, but it matched the data best. Yeah, but the thing is that it's not the wind as we see from the movie. The neutral wind at the balloon location is not a local phenomena. So it's not only from the location you see the ion drifts. It's actually from the polar region. Right? It's stirring the thermosphere in this way, and let's see the winds going there. Yeah, it'll be nice if you have the map, and then But we kind of get some confidence from the DMSP passes for this event. Yeah.
And related to that, you said that day is not stormy.
No.
But there must be something happening because it's like not like southward every day, right? Or equatorward every day.
Yeah, there's something going on here at -5 now. So there's southward turning. And if you look at the AE index, there's a substorm happening around 9 o'clock, and then we do see this discrepancy between the models and the data. So if there's energy coming through this process that cannot be modeled in the system, and we are missing this part actually right here. So what I'm saying that in the evening, the ion drag does a very good job in doing this.
So if you added outflow for the period where you had the substorm, you don't know if that would improve things or not.
Probably not.
Probably not, because you didn't improve it for the first 3 hours anyway.
Yeah, and it takes a while for the outflow to physically it takes a while for the outflow to get energized and go out, populate, and make the changes. while the storm I was looking at was like, hours, day. Yeah. Do you have a question?
What about adding monoenergetic and diffuse precipitation? I didn't
Oh,
understand that word.
these are in.
That's in there?
Yeah. So for this event, because we look at the driving conditions, they're very weak. So we do have some soft electrons down there, but they're not like huge. So these are the electron precipitations are included, but they're not the key parameters, at least for this model. I don't know. That's actually a very good question. So we'll have to ask Dr. Gang Lu.
That and my graduate students working on a next version of this, so with me on your data. So we're just kind of chugging along on that.
It looked like the CMIT with the outflow did such a significant improvement to matching the data. It made me think that, at least for storms like that, the energy coming from below and the gravity wave can't be terribly significant. Is that fair?
Yes, I agree. But I think that's actually depending on the time scale, right? So the bottom side is affected by the top side, right? When they got affected and they start generating all these things and going there. So there is actually a time scale thing, and that's not included here. And of course, if you put that in, and you might get some slightly different results. But for the top side, for the geospace drivers, I think that what's going on in the magnetosphere is the focus here. But you're right, the bottom side definitely matters. Do we have? Does the bottom side below change in TiGCM? I don't think so.
The large scales could be specified. The tides and the earth waves they could be specified, but maybe currently we don't have the spatial scale to specify the smaller scale.
Okay.